Thanks, everyone. As mentioned, I'm Payton Walker from Texas A&M University. So let's dive in to the paper about clean voice command injection attack, looking at passing it through multiple physical barriers. So this work was largely motivated, obviously, by voice assistant devices and smart speakers. Over the past, couple years, these devices just continue to grow in terms of the amount of capabilities and features they have. And there's also this idea of smart home environments that have been introduced where we can connect a central smart speaker as a kind of hub to different smart devices within the house, smart locks, smart appliances. And really, the more capabilities that are added and the more interconnectedness we can create with these, means these devices have access to more information and really have a lot more power. So that, mixed with the fact that they've become massively popular across the globe, means that there is significant increased security risk. All of that information and power that's given to these devices can also be given to a malicious attacker if they're able to compromise these systems. So previous research has shown that there are some command injection attacks that are reportedly successful. A lot of these involve kind of complex command audio generation. So things like hidden voice commands where you obfuscate an audio so that it won't be heard by other people, but could be understood by a smart speaker, or even more private ways of injecting commands, such as shooting a command through a laser or using ultrasonic frequencies. But really, up to this point, we hadn't seen an academic work that just looked at the potential, threats as well as limitations of just physical clean command injection attack through barriers, which is what we explore in this work. There's been multiple media coverage kind of alluding to this threat. A lot of it talks about, the safest place to put your smart speaker within a room. Particularly, a lot of these articles talk about keeping your device away from windows. There have been stories of smart speakers that are placed near a window, which could lead to someone just walking up and shouting a command through the window. And if it's heard, then the device will act on that action, and that way an outside person can control your smart device. So in this work, we designed clean voice barrier-based attacks, looking at 3 different types of barriers. We performed an extensive measurement study to look at different scenario parameters and different values to look at the potentials and limitations of this type of attack. We do a small demonstration to show that this attack can be launched remotely using drone technology. And from all of our results, we can make some informed observations about how the robustness of this attack could be increased, as well as some potential defenses to stop this type of attack. So this figure shows the different attack scenarios that we study. Firstly, across window. As mentioned, if the device is placed close to a window, then an attacker can stand on the other side of the window and either say or play some command audio through a loudspeaker device to get the smart speaker to perform some type of action. You can also perform the attack remotely, attaching a loudspeaker to a drone, which would allow the physical attacker to kind of stay removed from the attack setting. The next scenario or barrier we look at is the door in the across door scenario. And we find that most doors have at least some sort of small gap underneath the door between the base of the door and the floor, which actually allows quite a bit of audio information to pass through. And so again, if the smart speaker is within range of the door and an attacker can play audio, they may be able to get it to activate and perform an action. The last barrier is the wall in the across wall scenario. If you think of different kind of adjacent living scenarios, such as hotels, dorm rooms, apartment complexes, where separate living spaces share an adjacent wall, there's potential that if an attacker isn't on one side, you may be able to issue a command through that wall to affect a smart speaker that's on the other side. So in our threat model, the attacker, firstly, they can perform some initial testing to determine what type of smart speaker they're targeting. If they can't necessarily walk up to a window and look through it and see what device the victim owns, they can test this out using different wake words. For example, the Amazon devices only have 4 preset wake words that can be used. So an attacker can test all 4 of those to not only determine whether or not it is an Amazon device that they're targeting, but also what wake word specifically would get it to activate. Our attacker has a portable loudspeaker device that's loaded, preloaded with different wake word and command audios that correlate to the type of attack they want to launch and what they want the smart speaker to do. And the attack could also potentially be launched remotely if you put a loudspeaker on a drone and fly it up to a barrier. And the command audio that's used could either be recorded by the attacker themselves in their own voice. They could, enlist some other live speakers and record their voices, or they could even generate command audio using text-to-speech software. And because modern smart speakers today don't have a default voice verification system, meaning that they'll accept a command from really any voice as long as it's legible, means that there's really no dependence in this attack to use voice audio of the victim itself. So there isn't any effort beforehand to pre-record the victim's voice and either build a model that generates the command audio you want or record the command outright. And in that way, this becomes an untargeted attack. So an attacker that has a set of wake words and command audios, preloaded on a loudspeaker could really walk around, say, like in a neighborhood, and try playing it against multiple barriers and could potentially affect devices in multiple different places. So we look at set of multiple different experimental parameters. For the barrier type, as I mentioned, we look at the window, wall, and door barriers. We look at 2 different smart speaker devices, Amazon Echo and Google Home, for our potential targeted devices. For our command audio, we test audio from both male and female speakers that are either from sources of being recorded live or generated using text-to-speech. And we also tested 3 different volumes at which to play the command audio at 65, 75, and 85 decibels. And our last parameter is the smart speaker's distance away from the barrier. So all the way from 0.1 meters away, which is really just on the other side of the barrier, very close, up to 4 meters distance. For our audio samples, we used generated 3 male and 3 female samples from both the live and text-to-speech sources. And the audio included is custom for one of the 2 smart speaker devices that we tested. So a total of 24 audio samples were used in each of our barrier-based scenarios. The audio we used, as an example, is either the wake word, "Hey Google" or Alexa, and the single word disarm command. And this just represents a simple one-word command that an attacker may want to issue, particularly as it relates to the smart home environment. So if you have your smart speaker connected to smart locks or maybe security cameras outside the home, and that kind of security system is turned on, if you issue a disarm command, that could potentially unlock the doors or turn off the cameras, allowing an attacker to move around the house freely without being detected. And for running our experiments, with the barriers introduced, we did confirm that all of our command audio samples did have 100% injection success rates before the barriers were introduced, meaning that any difference or variation we see in injection success moving forward is strictly because the barriers were in place. For our equipment, we specifically looked at the Echo Dot 2 from Amazon and the Google Home Mini smart speakers. We used a commercial off-the-shelf portable loudspeaker from Sony. And to confirm that the audio was played at the correct decibel level for every experiment, we used a digital sound level meter. For the wall scenario specifically, we built a soundproof box and wall inserts. And we did this so that we could, one, test 2 different types of walls, but also have full knowledge and control over the types of materials that went into the walls that we were testing. So we had one wall insert that had no insulation and one that did have insulation. And on the right here, you can see we have the wall insert that fits perfectly snug into the soundproof box with the smart speaker on one side and loudspeaker on the other for these experiments. These 2 tables show our results for the command injection attack. We did also record the wake word injection results, and those are included in the paper, but obviously they're going to be either equal to or better than what we observed here for the command injection part of the attack. And one thing you'll notice is that we've trimmed these tables to remove any of the scenarios that have or showed no command injection success at all. So for example, we found that in all attack scenarios at all distances, command audio that was played at 65 decibels was not loud enough to activate or elicit a response from the smart speaker. So all of that, those blank rows were removed from these tables. But looking at the top table, which are the results for targeting the Amazon Echo, we see if we look at the highest performing speech samples that were used in our experiments, for one, using the first male text-to-speech sample, we can achieve 100% success at command injection at 85 decibels at the 0.1 meter distance. In the across window scenario, we can achieve 90% success using the second female text-to-speech sample at 85 decibels. And in the across door scenario, again, with that first male text-to-speech sample, we can achieve 100% success at 75 decibels up to 2 meters and 100% success at 85 decibels. 85 decibels up to 2 meters and 75 decibels up to a half meter in the across door scenario. For the Google Home, we also saw high success rates, again, looking at the best performing samples in the across wall scenarios, both 75 and 85 decibels, we can achieve 100% success. In the across window scenario, we can achieve 100% success at 85 decibels. And in the across door, we can achieve 100% success at 75 decibels up to 2 meters and 100% success at 85 decibels up to a half meter. We also performed some experiments using the drones equipped with loudspeakers. We tested 2 different types of drones, a Toy Sky quadcopter and a Holystone. Each of these has different kind of operating volumes. So when the drones are hovering and the propellers are spinning, obviously it's going to emit some sound. The Toy Sky quadcopter was a bit louder. It had an 85 decibel operating volume, and the Holystone had a 73 decibel operating volume. But naturally, with this introduced noise, we had to increase the loudness of the command audio that was being played. But again, if we look at the highest performing samples, we can achieve 100% success with the Toy Sky at 95 decibels, targeting the Amazon Echo Dot. And with the Holystone, we can achieve 100% success at 85 decibels, targeting the Amazon Echo with 2 of our text-to-speech samples, and 90% success at 85 decibels, targeting the Google Home. Another part of our work was to do some kind of initial signal analysis to see if we could determine if there was any indication why certain command audio samples weren't as successful or were more successful than others when we try to pass them through these different barriers. So on the left, we plot the power spectrum graph for 6 of the text-to-speech samples. The blue ones indicate samples that were had some success in command injection, and the red indicate samples that didn't have any success at all for command injection. And we found that when we zoomed in to the 6 to 8 kilohertz range, there were certain areas where there's a clear distinction between the successful samples and the unsuccessful samples, particularly finding areas where the successful command injection samples had stronger frequencies within those smaller ranges compared to the unsuccessful samples. So that may be an indicator as to certain characteristics that you could look for in text-to-speech or even live recorded samples that would allow them to be more likely to succeed in this type of attack. So to summarize, if an attacker wanted to increase the robustness of this attack and have a greater assurance of some success when launching it, our results show that really command audio should be played at 85 decibels or greater if the scenario will allow. Overall, we saw that text-to-speech samples performed better than the live recorded speech samples, which actually provides a lot of flexibility to an attacker. Obviously, if they can learn what type of smart speaker device that they're targeting beforehand, that gives them a lot of freedom to do some pre-tests on their own. They can buy a device that uses the same speech system as the one that they're targeting, test different text-to-speech samples, and really just increase their chances of a successful attack. And then again, back to the signal analysis, there were samples with stronger frequencies in the upper range that you could really look for when picking out the text-to-speech samples that you were actually going to use for an attack. For potential defenses, there are 2 that are more obvious. They're just about kind of trying to stop the physical phenomenon of audio passing through physical barriers. So obviously using materials with higher sound rating values. Our work, we found that STC values of 50 or higher would significantly decrease the potential for this attack to be successful, or using denser materials like concrete, double-layer drywall, or even sound dampening materials. What this would do is force an attacker to play the audio at even much higher decibel levels past the point that they could reasonably go undetected. And the other is obviously smart speaker placement. The distances we observed for that, if you place your smart speaker, half meter or greater distance away from the wall or the window, it significantly reduces the chances this attack will be successful. And with the door, there's a larger distance, you have to go greater than 4 meters away. Some more kind of technical defenses that we think could be implemented, firstly, are a machine learning model that could identify audio that has to pass through some sort of solid material or barrier before reaching the smart speaker. We know that there are changes that occur to the frequency distribution and power once they pass through that material. And so building a learning model that can identify those changes would help, would give a smart speaker the ability to reject any of those audio that are detected to have passed through a physical barrier. Another option would be source localization. There's been some research into identifying the distance and source of an audio that's received by microphone. So if you preload a smart speaker with the knowledge of what direction a barrier is relative to its location, as well as what distance away it is, and you use source localization, you may be able to determine that when audio came from the other side of a barrier. And again, the smart speaker could reject those samples. So to conclude, in this work, we presented BarrierBypass, and the attack that does clean voice command injection targeting smart speakers and passing it through multiple different physical barriers. The experiments we conducted did demonstrate the parameters that would allow for successful command injection. Particularly, we find that if you select the highest performing command audio samples, you can achieve 100% wake word and command injection for each of the different barriers that we tested. This attack we showed could be launched remotely or in person if you wanted to use a drone instead of being there live holding the loudspeaker. And then lastly, BarrierBypass, it exploits the lack of speaker verification, making it a much more robust attack compared to other command injection attacks that we've seen. And it also bypasses physical barriers, which we believe that would be a large hindrance to other command injection attacks that focus on very fine-tuned specific frequency distributions and powers, where if they had to pass through a barrier and that balance was messed up in any way, would significantly decrease its ability to be a successful attack. So all of that together makes BarrierBypass more robust in that sense compared to other attacks that we've seen. And that concludes my presentation. Thank you for listening, and I'm available for any questions.
Questions for our speaker? So Payton, while we get the next talk set up, if you wouldn't mind closing your slides and your share screen so our next presenter could start. This is Brad Reaves, the session chair, by the way. I've got a question about how you were looking at your different text-to-speech samples. So the graphs you showed were the spectrum for the entire phrase, but when you look at voice data like that, you lose a lot of information. I'm wondering if you looked at the spectrograms or analyzed formants or anything to look for speech characteristics that might have differentiated the different clips.
Sure, yeah. So we looked at the, again, these were the text-to-speech generated samples, and obviously, the machine-generated samples include a lot of audio data and go across a frequency range beyond what just normal live recorded human speech would. We did look at just regular spectrograms, but we didn't find anything that was very distinguishing. A lot of it's very uniform because of the machine generation nature of those samples. It wasn't really till we got into the power spectrum that we started to identify some of those differences that did exist. And that part of the work was really just kind of an introductory to indicate that some future work could certainly look deeper into analyzing those samples. We did isolate specifically the word, so the single disarm word in our phrase, so it wasn't the entire clip of wake word, bit of the pause command. It was just the command section of it, because we did find that wake word injection was largely more successful throughout. So yeah, did that answer your question?
Yeah, fantastic. So let's thank our speaker again.
Thank you.